All right, scholars, welcome back to our final lesson in Unit 1. It's been quite the journey over these past 3 to 4 weeks. It's been 3 weeks. We have arrived at our final topic, which will be lines, and refreshing your memories regarding everything that you might have been introduced to in Algebra 1. Our learning objective for today's video content includes we are learning to graph linear equations of the form ax plus by equals c and interpret points on the graph in context so I can understand that different forms of a linear equation can give different insights about the relationship it represents and about the graph. I'll know I've got it when I can analyze how the numbers in an equation ax plus by equals c are reflected on its graph and are related to the rate of change in the relationship. We have some vocabulary words over here that you are to define. And let's jump into lines. Okay, so when talking about slope, why did slope originate? Slope came to fruition because society, or civilization I should say, because I don't even know if we could define what the earliest forms of human beings were as a society, but civilizations needed a way to measure the steepness of a line or how quickly it rises or falls as we move from left to right. Applications of slope include, but are not limited to, the building ramps for accessibility, the pitch of a roof to protect a home, or the grade of a road so we can travel to and from different locations, like traveling up and down a mountain. The slope of a line is the ratio of its, by its I mean the line, to rise to run. So what does that actually represent? Well, we're going to have to take a look at our diagram over here. Okay. When we're calculating the slope, it involves 2 points on that line. So in using the word rise, we're looking at the change in height. Once again, is represented by the y coordinate. I should say, I'm going to give a lot of space, vertical position. So the change in the vertical position of the 2 coordinates, and the run would be the change in the horizontal position, which is the x coordinate. Now numerically, how do we determine the change in vertical and horizontal positioning? We would take the coordinates. I knew I was going to run out of space. There we go. Minus, no, not, there we go, minus y sub 1. So we're going to take our 2 y coordinates and subtract them. We're going to take our 2 x coordinates and subtract those. Calculate our slope. Do you this y2, y1, x2 minus x1, all it is simply doing is identifying one set of coordinates and distinguishing it from another set of coordinates. Okay, if you wanted to do y1 minus y2 divided by x1 minus x2, you are more than welcome to. Just be sure that whatever coordinate you select first is both the first value in both the numerator and denominator. Okay. So using this graph below, please draw 4 lines, one with positive slope, one with negative slope, one with 0 slope, and one with an undefined slope. As we had said in the previous slide, we interpret lines in the same manner that we read text, left, right. So if we wanted a line to have positive slope from left to right, our line should be trending upwards. Whereas lines with negative slope should slant downwards. Horizontal lines, like the floor of your home, the sidewalk, the hallways in our school building, are nice and comfortable to walk on and possess a slope of 0 since there is no steepness. Right? Steepness would indicate a vertical change. Whereas vertical lines, much like the walls behind me, go straight up and down. The only human being, I don't even know if you can classify him as a human being anymore, but the only person that I know who is able to scale walls is Spider-Man. So we see that lines that are vertical have a slope that is undefined because it is not a natural phenomena to be able to scale a vertical wall, as there is no horizontal change leading to a computational error. That computational error is dividing by 0. Okay, that's our conceptual understanding regarding lines. So once again, please make sure you draw your 4 examples. I'm going to skip through this because it's definitely something that have the utmost confidence that you're all able to do. If you're not, you can definitely review it together. Okay, now getting to the good stuff. So while I am aware, we can obviously just memorize the avalanche of formulas used to describe lines. We are going to rely solely on the most crucial component of a line, and that's its slope. That's why 2 slides ago I had you draw lines contingent upon the slope of those lines. So when we're defining an equation for a line, we require 2 components, slope and no, it's not the y-intercept, coordinate, aka a point. I would say the most essential form of a line would be one that we in the math realm notate as point slope form. And it all begins with the formula for slope. Okay, the formula for slope involves 2 points. Okay, but when we want to craft an equation of a line, we only require 1 point and the slope. So rather than, here we go, I'm going to delete that second coordinate, okay, and replace it, and it becomes an arbitrary point. So any point on our line, which is how we craft the equation for a line in point slope form. So if I wanted to rewrite this equation so that there was no denominator, as you would with any equation, you would multiply both sides by the expression x minus x sub 1, because that is what we are dividing by. Because mathematics is a staunch advocate for equality, we make sure we do that operation to both sides of our equation. As we can see, the right-hand side will simplify to y minus is equal to slope, represented by m, times x minus x sub 1. And there you have it. The formula, I like using the word formula, the form of a line in point, int is an integral symbol, so we're going to have to just type that one, point slope. I'm going to leave b and c for you, but we will rewrite this expression into slope-intercept form, which I'm sure many of you can recall without even thinking. Before we do that, the general equation of a line is given as, no, I don't want the draw tool, ax plus by c 0, where a and b are constants that are obviously not 0. Right, so going back to my original point, how can we rewrite the formula for slope in slope-intercept form? We would obviously follow the same pattern that we did before. Multiply both sides of the equation by the denominator. That way it is removed. And we're left with y minus y sub 1 equals m times the quantity x minus x1. You could distribute in this situation, and you'll come to find that y minus y1, y sub 1 is equal to mx minus m times x sub 1. Now this value here are defined numbers. Therefore, it is an actual numerical value. And if we add y sub 1 to both sides of my equation, we would be able to combine these two values. On the left side of the equation would be simply a y. So we're left with what you have probably been ingrained to recant like a cult, y equals mx plus b. But b is actually the sum of your y coordinate and your x coordinate multiplied by the slope. The things you come to know. Okay, but that's how we can manipulate. That way we don't have to worry about memorizing everything. And instead we can say it all boils down to slope. That is our focal point here. So I ask you, oops, let me change those. Do the same with B and C. However, you should be able to modify those formulas for slope because I'm telling you that you're working with a vertical and horizontal line. Okay, so think about what are the properties of a vertical line? What are the properties of a horizontal line? And see if you can modify them accordingly. We know that two non-vertical lines are parallel if and only if their slopes are equivalent. That's awkward. I'm going to have to delete that top part because that's definitely not for this slide. Okay. So we're going to avoid the proof because the proof involves geometry and congruent triangles, but you can take my word for it. But we would probably use our hypotenuse leg theorem here and demonstrate that the distance between A and B and one of its corresponding legs is equivalent. Right. So in this task for checkpoint 3, we're going to find an equation of a line through this point that is parallel to this line. Okay. So remember, equations that share or are parallel have the same slope. We currently do not have a slope here. So you need to first identify what the slope is, and then coincidentally, you will have the slope and you will have the point. And in the previous second and third slide, you have two forms of an equation that will allow you to create a new equation. Now, as far as perpendicular go, two lines with slope m1 and m2 are perpendicular if and only if the product, so m sub 1 times m sub 2 is equivalent to negative 1. And what we mean by that is their slopes must be negative, so opposite. Let's use that word instead. Opposite reciprocals. So M2 really needs to be equivalent to the negative or the opposite of the reciprocal of M sub 1. Okay. With this being our final checkpoint, I shall assist you with this, and then we'll pause there as the enhancement opportunities are on our next slide. So we're going to find an equation of the line that is perpendicular to this line, 4x plus 6y plus 5 equals 0, and passes through the origin. I'll let you work out the redistribution of terms, but our equation, slope-intercept form, is negative 2/3 x minus 5/6. All that algebraic manipulation up here in the dome. So the slope for this is currently negative 2/3. In order to have a perpendicular line, I need the opposite. So m sub 2 is going to be equal to the positive. I don't necessarily need to include that. Reciprocal, 3/2. And I know that it needs to pass through the origin. So the good thing about that is if we're passing through the origin, the y-intercept will be 0, which brings me to the equation perpendicular line. So I'm going to say actually y sub PER for perpendicular is equivalent to 3/2. And if you don't believe me, take those two lines, punch them into Desmos, see what they look like. Maybe I'm wrong, maybe I'm right. Let me know about it tomorrow. But that'll do it for this video. Thanks for staying tuned.